386.
You really didn't have long. Yeah, I bet you forgot too. You just thought it.
It's like a spelling bee, but on steroids. Yeah, an integration bee.
I watched it like 2 years ago, so I've been waiting.
And so now you know. Yeah, that's so nerdy of you.
Yeah, I don't know why I watched the whole thing, but
Could you do some of it? No, but after this semester.
Like they had different whiteboards.
Yeah.
They would like go across 5 different whiteboards to do.
So it's like a spelling bee, but calculus integration bee, and they get problems, and each it's a participant competition thing. It's
Yeah.
Did you say they had multiple whiteboards each?
Yeah.
Why is it like a spelling bee?
Like 8 layers
It's
of
not a
whiteboard.
spelling bee. It's an
She's saying like why is this
Oh,
like integration?
I don't even know. Okay, so here we are. This is now chapter 5. Hey, in this is your pacing thing that we've had all year long. Y'all remember this? We are now starting unit 5. But if you look at these units, this is fast. Okay? We are well over halfway through calculus. We will be covering these last 4 units really quickly. Okay? Like I said, we'll be completely done with content by spring break. Yeah. It's going to fly. And a lot of this you've already kind of dipped into in physics because we had to. I told you we had to get the cart before the horse a little bit. And so some of this material is going to seem like, I already know how to do this. I would encourage you to stay hooked up, stay plugged in, because the work that we did in this stuff in physics is going to be so minimal as far as your understanding. Okay, so we really want to deep dive here, and we want to get kind of to the root of the issue instead of just barely covering the surface. Okay, so even if it feels like at some moments, I've already seen this before, remember that 3 of you have not seen this before. Okay, so we're going to have to make sure that Yaya and Sophia and Brooks don't get super left behind. And secondly, it will be good for everyone to understand all of the material. Okay? All right, so this title is called Antiderivatives. And when we were so our whole first semester, the focus was on differentiation. The whole thing, like from the beginning, learning what is a derivative, why do we have it, remember our tangent line problem, the velocity problem, and then going into, okay, we did limits for half our lives, and then we learned the power rule, right? And then after we did the power rule, we learned the product rule and the quotient rule and the chain rule. And all year long, we developed these tools for differentiation. And then we applied it. We applied derivatives when we were doing related rates. We applied derivatives when we talked about optimization. We applied derivatives when we did all of the curve sketching that we ended with. And we used the first derivative test to tell when a function's increasing, decreasing. We use the second derivative test to tell whether a function was concave up or down, right? We did all of that. All of the focus all semester was derivatives. This semester, all of the focus is going to be all of that in reverse. Antiderivatives, okay? Integration. Finding out instead of how is the curve behaving, we're looking at what's happening under the curve, okay? And it has its own application. We'll actually get into more of that in this slide deck in physics that we just started. Okay, so a function f. So this is definition 1. This is on page 386. It says a function f is called an antiderivative of f on an interval I if f prime of x is equal to f. Okay, so a function f is an antiderivative of little case f if f prime of x is f of x. So I can say that this big capital F is an antiderivative if, when I take its derivative, I get back to the function f. That's how I know I did it right. If I take the derivative of what I think to be the antiderivative and I get the function, then I know it's truly the antiderivative. And we've looked at a couple of things. For instance, let f of x be x squared. Okay? And the first time we looked at this, we said, well, maybe an antiderivative of f of x would be x cubed. Because if it feels like with the power rule that I drop the power and kind of go forward, so it feels like maybe that's the way this should work too, right? I could just add one back. No. Because if I take the derivative of f, my capital F, what do I end up with?
3x.
The derivative, f prime of x, would be 3x squared, which is in fact not equal to f of x, which was just x squared. Okay, so we know that that's actually not the antiderivative. What do we have to do instead?
Divide.
Yeah, so I don't just get to add one to the power. I then have to, so let's try this. Then have to divide by that new power. The reason being, when I take its derivative, that guy's got to go away, right? So now let's try, I think that this is f of x, capital F. I think this is the antiderivative. Let's take its derivative and see if we do get back to our f. Okay, so how do I differentiate 1/3 x cubed? How do I take its derivative? Use the power rule, right? So I'm going to use 1/3, and I'm going to multiply that by 3x squared. And what happens with the 1/3 and the 3? Those cancel. So f prime of x is x squared, which is in fact equal to the f of x that we began with. Okay, so that's how I know that is actually the antiderivative. Cool. Is that the only antiderivative?
You can keep going, probably. Like, you can derivative. That's what you mean.
Like, there could be
Okay, there could be
a term that gets canceled.
there could be a term that you lost.
Yeah.
There could be some number out there that just kind of we lost it, right? So I say that f prime of x is x squared. That checks, right? We're saying that x cubed over 3 is an antiderivative, but that leads to the argument that maybe
There were like 4 that you added.
what if I say this is an antiderivative?
That is also a...
How do you know? How do you know if it's an antiderivative? If I take the derivative of it, if I take g prime of x, what do I get?
X squared.
X squared, which is f of x. So it could be, if that's the case, I could have infinite number of antiderivatives, right? Who's to say what my number needs to be, that it's plus 28?
The problem does.
Could it be minus 4? Could it be plus 7?
Any constant.
Any constant, okay? So this leads us to theorem 1, which says if f is an antiderivative of lowercase f, then the most general antiderivative is f of x plus c. Plus c. So we put this plus c at the end to handle the fact that there could have been a constant, right? Could have been a constant. So who in this classroom, I think it's going to be Thomas, who is the most able to remember things that will remind us all? Yeah, you tell us every day calculus is red. So I'm thinking it's going to be you. If Nikki was in here, I'd make it be Nikki.
I got it.
Seth's got it. Okay, so one of you, and I don't care who, is going to be called the sea monster. Get it? The sea monster. Last year it was Samantha Price. It was Samantha Price. So your job, sea monster. Do we trust Seth?
But my name starts with a C.
Sometimes Seth doesn't sleep.
What is mine going
What do you mean?
Brooks. It may be Brooks. This could be how we keep Brooks awake. Brooks. Brooks is going to be the sea monster. Okay, so your job, anytime that we're taking the integral, okay, anytime that we are doing an antiderivative, if we don't know on an interval from 0 to 4, or we don't have any more information than that, this is called an indefinite integral. Your job is to say plus c. So that all of the rest of us remember when we're doing this, there is an arbitrary constant out there, plus c. Because if we don't put that c on the end, we're wrong with our antiderivative. Because we see that it could be any number. Okay, so we have to put the plus c. Don't forget the c.
So after x squared?
After x squared. So if I'm finding an antiderivative, then I write plus c at the end to acknowledge the fact that there was a constant out there. Okay? If you don't have it, you're going to get the problem wrong.
So after you lose the constant, it's plus c?
Plus c. And that makes you understand that there could have been, it didn't have to be, but there could have been, or it could be 0. Could have been a constant back there. So we have to have the plus c at the end after we anti-differentiate. Okay? So it's a heavy load, Brooks. But we're counting on you.
I think everybody's going to remember, but...
Yeah, it will.
He's not gonna
It
say
will.
and then
It
we'll
will.
make fun
So
of him.
Brooks is the sea monster. That's how this is going to go. Sam Price was perfect because she would just yell at us, plus C! Okay, Sam. Okay. It was great. And I had a kid this year test, and he missed a problem because he didn't put the C. And he was like texting me, I needed Sam. I lost the C. So this is like in your future, understand how important that piece of information is. I did want to show you a picture here that's in the textbook, and this is mostly for our let. But this is a great conversation. Theorem 1 says, if f is an antiderivative of f on interval I, then the most general form is going to be f of x plus c. But you can see that graphically here. Can you see these beautiful graphs? The only difference in any of these graphs is the constant. And you notice that all of them are antiderivatives of x squared. All of them. So that constant is free floating, could be anywhere. All of these count as antiderivatives. Are we good with that? Okay. What time does this bell ring today? 1:05? Sweet. All right, so we're going to jump into example 1. And example 1 says, find some antiderivatives. Find some antiderivatives. So here we go. It says, find the most general antiderivative of each of the following functions. Okay. So for part A, if f of x is sine x, then what would its antiderivative be? F.
Negative cosine
Yeah.
plus c.
Negative cosine x, good, plus c. Negative cosine x, because why? Because if I take the derivative of negative cosine, I get sine. We're undoing it. We're going in reverse. Cool? Okay. So here's letter B. Let f of x be 1 over x. And so another way to ask yourself is, 1 over x is the derivative of what? Natural log. And so that's how I do it. I say, I'm looking at this function, and I know that it is the derivative of something else. So 1 over x is the derivative of the natural log. So the natural log of x would be the antiderivative. Okay, we want to make sure when we do the natural log that we understand it could have been positive or negative. And so we handle that by putting absolute values because we know we can only log a positive. Natural log of x, Brooks? Plus c. It's the sea monster. If you don't got it, you're in trouble. And then this is the last one, letter C. Let f of x be a polynomial function. X to the n power. under the constraint that n is not negative 1. And I'll walk you through that in just a second. Natural law, or x to the power of n.
N minus 1, N plus 1.
N plus 1. So x to the n plus 1. And then what? Divided by n plus 1. You're going to divide by the new exponent. Ladies and Brooks that have been gone or not in physics. This is the power rule backwards. You add 1 to the exponent, but then you've got to divide by the new exponent, n plus 1. And we saw that y is the antiderivative of x squared, not x cubed. Because if I don't divide by the 3, I don't get back to where I started. Okay, so add 1 to the power and then divide by the new power. Under the understanding that this is not n is not negative 1. Okay, so let's start out. This is right, almost right, Brooks. What are we missing here? Plus c. Okay. Under the understanding that n is not negative 1. Okay, so let's pretend that f of x had said x to the negative 1 power.
It'd be to 0, x.
Right. So if I treat this like I'm going to do the power rule backwards and I add 1 to it, then I get f of x equals x to the 0 power divided by 0. Yuck. Bad. Bad. This is not it. Okay? So, and you'll spin this web. I do this all the time. I'll get x to the negative 1 power, and then I'll do this exact thing, and then I'll think, oh, what happened? So let me show you. This is actually not it. Bad, 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 bad. Watch this. Let me open your little eyes up. X to the negative 1 power. If it's a negative power, what can I do with it? Put it in the basement. Hey, guess what? We already did that one. Oh. And I promise you'll walk through this a million times before you can recognize that x to the negative 1 power is 1 over x, whose antiderivative is the natural log. We already did that, right? But this is going to happen to you, and you're going to get x to the 0 divided by 0, and you're going to say, ha! And then you're going to, oh, yeah. Okay, so this is one of those things. You'll go through it. It'll be fine. Any questions on those? Okay, so I'm going to make you do one last thing. What time does the bell ring? 1:05? Okay, so one more thing before I cut us off today. There's a table of information on the next page, page 388. And I would love for you to get all of this information written down.
The table?
The table. This is a table of antiderivatives, basically. And then I'm going to add one more thing to it right here. This is important.
Why is the word particular there?
To obtain a most from a particular one, add a constant or constants. I don't know.
Particular antiderivative?
Yeah, so add a constant or constant. So sometimes the book's going to tell you an initial value, and that'll give you your constant.
So just that side of the table?
Mm-hmm. So, yeah, if your function is a constant times the function, then your antiderivative is the constant times the antiderivative. That's what happens with the constants. I think it's interesting if you read the antiderivative and you thought to yourself, how would I take the derivative of those things? Then that's what's on the left, the function. But for now, we're reading it forward, so we start with the function and then our antiderivatives in the column. And I'm going to stop recording right there. You guys can finish writing this all down, and we'll pick up here tomorrow.